Hi, everyone. My name is Stephanie Snyder. I am an undergrad at Penn State going for math and physics. And today I wanted to give a little talk on how fiber optics work from a physics standpoint. Okay. So the first thing we need to talk about is reflection. So we're dealing with a flat surface, in this case, a mirror, and everything that we measure is based off of what we call a normal line, which is just an imaginary line that is 90 degrees or perpendicular to the surface that we're dealing with. So whenever we think of light, we think of it as a ray. And so our light ray comes in at a certain angle. We call this the incident ray and the incident angle. Now the incident angle is measured off of that normal line that we define. Whenever we're dealing with reflection, our incident light ray bounces back at the exact same angle that it came back in at. So our incident angle is equal to the angle of reflection, which is what we define it as. And this can be seen with mirrors, like I said, but also very still water, as you can see in this image where the mountain is perfectly reflected off of the water and you see the reverse image. Now we can also talk about refraction, where we still have that normal line on our boundary. But in this case, we're dealing with something like a piece of glass rather than a mirror. So we have our incident light ray coming in at our incident angle to the normal line. And part of that light ray is reflected back, as in the case with the mirror, but some of the light passes through the boundary and it's refracted. So we still expect the angle that is reflected to be equal to our incident angle, but our refracted angle based off the normal line might be different. And we can find this by comparing indices of refraction of the material, where the medium or the material has a certain index of refraction. It's just a number that we give to it. And we find that value by a ratio of the speed of light in a vacuum, which is c, to the speed of light through that certain medium. And that's found by basic calculations. So we can apply that to get this ratio here, n2 sine of theta 2 equal to n1 sine of theta 1, which is the index of refraction of our medium multiplied by the sine of the refracted angle times our first medium. Let's say in this case, it's going through air first before it hits the glass. So that would be the index of refraction of air multiplied by the sine of our incident angle. So now we talk about total internal reflection. So we have a certain angle called the critical angle, which once again is dependent on the different mediums. But this angle tells us if the light ray will reflect or if it will refract. It's sort of a cutoff. So if our incident angle is larger than the critical angle, then total internal reflection will occur. And that is just whenever the light ray kind of ping pongs back and forth off of its boundaries and it'll only reflect. There is no refraction happening. And this can happen with any sort of medium. It doesn't have to be a mirror. It could also be a piece of glass as long as the incident angle is larger than this critical angle. And so if the incident angle is less than the critical angle, what will happen is that it will reflect, but it will also refract. And because of this, it's losing light more and more until it eventually will die out. So for total internal reflection to occur, we need to make sure that we have the right indices of refraction to make sure that this incident angle based with the critical angle can allow reflection. So a fiber optic, this is a cross section, is made up of many, many layers. But the main two that we're really looking at are the most inner two. And so the innermost layer is called the core and the second most inner layer is called the cladding. And it's important that the core has a greater index of refraction than the cladding does. So what's happening is that we send our incident light ray through the core. And because the index of refraction is greater, than the index of refraction of the cladding, this can allow total internal reflection to occur. So basically the way a fiber optic works is that we shoot a light ray through the core and it ping pongs back and forth off of the cladding as its boundary. And so it doesn't diminish and the light continues to pass all the way down until you see it on the very end. So yeah, that's about it. Thank you.